Hello class, good evening. It is evening for me as I'm making this video for you. I'm sorry we were not able to meet on Wednesday. I did miss y'all. It's hard to make a call when a storm's moving in the morning, so it was better safe than sorry to just not have class. But we will be having class the first on the 6th, I believe is the day we return in January. I will have a substitute on that day. So make sure that you have your test ready to turn in on that day. Also, and I will be sending that test to you in the next couple days. Also, make sure that you have read Chapter 6 and that you're ready for a vocabulary test on Chapter 6, okay? Chapter 6, a lot of times what I will do at this point is I will give you an option between doing an open book quiz or a closed book quiz. Usually the open book is a little bit more detailed, takes a little bit longer to do, but you do get to look in your book. The closed book one, if you've studied and you're ready to go, you probably would prefer to do that one if you've studied it and you're prepared. So I thought today that I would just go over the review sheet that I gave you to study for the test. If you do well on this review sheet, you will do well on the test. And I'll also go over a couple of them on that worksheet, maybe 3 or 4 of them, and let you work the rest of them on your own. Just do your best on that sheet and turn it in. I won't be grading to see if they're correct. I'll be grading to see if you did it and if you were trying to get it right. So let's go ahead and review, starting with the definitions. It's very important that you know the definitions. This is not going to be matching. You have to actually spit these definitions out. And so for a covalent bond, you need to know that is a chemical bond that is made by sharing electrons, okay? That's your covalent bond. I don't know if I said chemical bond. Yeah, covalent bond is a chemical bond that is made by sharing electrons. The atomic radius is the distance from the center of the nucleus to the atom's valence electrons, because the valence electrons are hanging on the outside there. Electronegativity, a measure of how strongly the atoms attract electrons in a covalent bond. Polar covalent bond, it's a covalent bond in which electrons are not shared, which means that the purely ones, the pure individuals, they share their electrons equally. So a covalent bond in which the electrons are shared equally. Make sure that you know those definitions. If it's not word for word, that is okay, but you need to definitely understand the definitions well enough to be able to tell me what they are. Also, I want you to understand what a homonuclear diatomic is. That was not put on the sheet as far as definitions. I had you list them for me, but I do want you to know what a homonuclear diatomic is. So you will have to list the 7 homonuclear diatomics, and you can either write them out or you can list them this way. You can H2, O2, N2 for nitrogen, so hydrogen, oxygen, nitrogen, bromine, fluorine, chlorine, and 1, 2, 3, 4, 5, 6, which one am I forgetting? Iodine. There it is. Okay. So there's your 7 of them that you want to be able to know and list. The next question on your sheet, it was a little bit confusing maybe to some of you because you were thinking, when I asked you what the chemical formula was for the element fluorine, you were thinking, well, it's just an element. There's not a chemical formula. And what I was trying to get you to think of with that is that right here, did I not write that? Why did I put an L there? I apologize. This is what fluorine would be, F2. You always want to write that because it is a homonuclear diatomic with the 2. Okay, make sure you don't put an L like I did. I don't know why I did that. It may be because it's 6 in the evening and I've been busy today. So either way, I don't think that I need an excuse. I think I'm just ditzy all the time. But there it is, fluorine, F with the little 2 there because it is a homonuclear diatomic. Next thing that we want to talk about was the atomic radius and the electronegativity. Now I've got my periodic chart here in the book, and you may use your periodic chart for your test. That's perfectly fine. If you've got a copy of it or whether you just want to use this part of the book, that's okay to do that. Knowing that the electronegativity and the atomic radius are opposite of each other, electronegativity starts at the bottom and it increases as it goes up and it increases as you go from left to right, just like reading a book. So it's smaller down here, it gets bigger, smaller here, and gets bigger. Now this is still bigger than down here, but this is smaller than over here. Okay, so up and over for electronegativity. For the atomic radius, it's the opposite. as you go up, it decreases. The atomic radius gets smaller. And as you go to the right, it gets smaller as well. So on your review sheet, I asked you to order the following terms of increasing atomic radius from smallest to largest. So we have phosphorus, magnesium, aluminum, and argon. And if you look on your periodic chart, remember we're going from the bottom up. Starting at the bottom, it's bigger and it gets smaller as you go up with the atomic radius. So argon would be your smallest, phosphorus, aluminum, and then magnesium. Okay. Now looking at the electronegativity from lowest to highest. We have strontium, radium, and magnesium. Now, if you'll notice, they're in the exact same column, and radium's on the bottom, and with electronegativity, it gets bigger as you go up. So this is kind of easy to see since it's in the same column. So radon would be the smallest, then strontium, then magnesium. So that would be the order that you would list it in, okay? Which atom has the greatest desire for electrons? Well, as you look at these three, you want to see which one's the furthest to the right. Remember that all those nonmetals, really, they're the takers. They desire to have more electrons. They have a greater desire. So the one that is the furthest to the right on your periodic table would be bromine, or bromine, however you like to say it. Number 11, a student dissolves alcohol, which is a polar compound, in distilled water. In another container, he dissolves sodium dichloride in distilled water. Both of them are in distilled water, so we're basically looking at the compounds of sodium dichloride and alcohol. Will either of these solutions conduct electricity? And if so, which one? Well, as I look at those two compounds, I see that sodium dichloride has a metal in it. And I know that that makes that an ionic compound. And ionic compounds will conduct electricity in water. So yes, there will be one that conducts electricity, and yes, it is the sodium dichloride. And the reason why is because sodium is present and sodium is a metal. So you'd want to be able to understand that. I had you draw a soap molecule, and I'm not going to draw one on the board here, but when you do your test, I'm trying to decide whether I'll have you draw one or whether I'll put a couple pictures and you choose which one it is. I'm not going to grade you on how great this molecule looks. I mean, don't worry about the art part of it. What you do need to know is that the soap molecule is a longer molecule that is attached, and you can study this on page 152. And the important thing about that is it's important to have the ionic end with it. So meaning you have to have a positive and a negative charge. So if you draw a short one, you put 3 or 4 little molecules together, that's not long enough to be a soap molecule. It has to be a long one. And then once you draw that long molecule, don't forget where you put your charges. And I'll let you study page 152 so you can see that as to where you would put your charges to show that, okay? Hydrogen has an electronegativity of 2.1. This is number 13. The electronegativity of chlorine is 3.0. The electronegativity of tellurium is 2.1. Which of the following make a purely covalent bond? Well, the ones that are going to make a purely covalent bond are going to be the ones that share the exact same electronegativity. So obviously, we notice that hydrogen and tellurium would do that, so that would be D. But there's one more, and that would be hydrogen and hydrogen. If you had 2 hydrogen molecules, they both have the same electronegativity. So C and D would be your answers on that one. Next, we're going to go ahead and go over number 14, determining the Lewis dot structure and shape, and whether or not it's polar or nonpolar. Okay, so we have silicon tetrachloride for this because there's 4 of the chlorines, and so silicon's going to be in the middle. And I'm going to go ahead and draw my chlorines because there's 4 of them on either side. And I'm going to start with my silicon. Basically, I've got my little dots for my silicon, and then I come in, chlorine has 7. So I'm going to fill that in, 1, 2, and I'm going to put that there, 4, 5, 6, 7. That forms a bond there. Okay. 1, 2, 3, 4, 5, 6, 7 forms my bond there. 1, 2, 3, 4, 5, 6, 7 forms my bond there. 1, 2, 3, 4, 5, 6, and 7 forms my bond here. So here's my bonds. Now, if I were to go ahead and draw this kind of in a three-dimensional way that we have some pull, you would kind of have it like this. It's not art here. To kind of show that that's a three-dimensional thing. Now we see that there's 4 sides, so the shape of this would be a tetrahedral. One of the things to determine whether this is polar or non-polar, if we have symmetry, equal pull on all sides, then we're going to have a non-polar compound. This particular one, the chlorine, is pulling in all 4 directions, so it is non-polar. Okay. One of the things that that you won't have access to on your test, so I'm going to try to keep it simple for you on your test so that you'll know. But a lot of times you can determine, unless it's obvious that there's symmetry, like on a linear one, you can tell that there's exact pull and that makes it nonpolar. One of the things that will help you know whether or not a compound is polar or nonpolar is that if the electronegativity, if there is a greater difference, then if the difference is greater than 0.5 in the electronegativity, then most of the time you're going to end up with it being polar. Now that is not necessarily, if you're seeing a symmetrical pull, then that necessarily doesn't apply, okay? But a lot of times you can look at that and you can determine that if the difference between the electronegativity is greater than 0.5, and you might say, well, how would I know that? Well, on that chart for you, the electronegativity, they kind of rounded it up in your book. They didn't give you exact amount, but the number there, it had commas, and the comma actually represents a decimal, and that would kind of help you out a little bit. And that's the one on the electronegativity chart, okay? All right, next one, we're going to go ahead and look at phosphorus trifluoride, okay? So I have phosphorus here, and then I have, let's go ahead and draw my molecules here so I can bond these together. I have 3 fluorines. Okay, 1, 2, 3, 4, 5, 6, 7 for my fluorines. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Go ahead and do my bonds. Let's make sure that everything has 8. 1, 2, 3, 4, 5, 6, 7, 8. And we know that the fluorines do. So on this particular one, I have these 2 electrons that are hanging out here. That's fine. They're paired up together, so it's okay to have them there. You wouldn't want one hanging out by itself, but he's paired, so he's fine. And so this type of shape, you'd be kind of looking at something like this. And one of the things that we notice here, even though this is fluorine and it's pulling, it's asymmetrical, meaning it's not pulling equally. If we had another one up here, if this was a tetrahedral, it would be pulling equally, and that would make it nonpolar. But because this is asymmetrical and it's not pulling exactly to cancel out,